All right, then let's start our today's session. So, this is going to be the second class of the next unit, that is magnetism and electromagnetism. So, in the last class, we saw a few things. We saw a few things related to the magnetism, and we are continuing this part only. Third lecture of this unit will be based on electromagnetism. We'll talk about that in the next class.
Mhm.
So, in today's class, we are going to look at the following topics: solenoid, toroid. We'll talk about Lorentz force. So that Lorentz force is something, basically the magnetic force you can say, or
Mhm.
you can say it is the force which is experienced by a charged particle when it is placed in electric field as well as magnetic field. So because
Mhm.
of the two fields, the force which a charged particle will experience, that force is called Lorentz force. We'll talk about that also. Then we'll be looking at what is a magnetic force on a moving charge. So if a charged particle is actually moving, what kind of force it is going to experience, what magnetic force it is going to experience. Last, we'll be talking about electromagnetic forces and then a special device which is known as cyclotron, which is being used to accelerate a charged particle.
Mhm.
Like, in order to understand it, let me give you a very simple example. If you know about the alpha particle scattering experiment, which was performed by Rutherford, in that experiment, he used alpha particles as the source of charge, and he bombarded these alpha particles onto a gold foil. Do you know that experiment done by the Rutherford?
No.
All right. In order to understand the structure of atom, Rutherford performed an experiment, and in that experiment, he bombarded alpha particles onto a gold foil. So during this experiment, he actually bombarded alpha particles, or you can say the high-speed alpha particles. So in order to give those alpha particles that much high speed, the device which he used is cyclotron. So we'll talk about that device also. Let's start our today's session. The first is solenoid, as we have already seen this in the last class also. Solenoid is a device, you can say it is a component which is being used in the circuits as it can generate magnetic field when a certain current passes through it. So when a current passes through the one end of the wire is attached in such a form that it will form helix. This
Mhm.
shape is something we call helix. And I also explained you this thing that that spiral shape is something which looks like this. This shape is something we call spiral. And the
Mhm.
shape which this component has, this is something we call helix.
Mhm.
So we call it helical shape also. So when one end of the wire receives current, so that current will pass through each and every coil.
Mhm.
So this is something we called or we refer as coils. The current will pass through these coils, and when the current passes through these coils, what happens is that there is a magnetic field which set up through this coil. Or what we experience here is that this magnetic field which is being present inside the coil is something which is only present inside it, not outside it.
Mhm.
So that what makes it, you can say, a very special device. And you must have seen some videos where there is a spring, and when you just put a battery onto the one end of the spring, the battery moves automatically to the other end. Have you seen such videos?
Uh, I think so. Maybe I don't know.
I guess you must have seen it because this was something which was like very popular. So what happens there is when you put a battery at the one end, and again there is no current flowing through the conductor, but this battery is a source of potential. So because
Mhm.
of this potential, there is a flux which got induced into the coil. We'll talk about that those terms as well. And because of this, there's automatically some force acts on it, and because of it, it suddenly moves. It's automatically moves.
Mm.
So this is something which we are going to use here also. So when we talk about that the magnitude of this magnetic field, that magnitude of magnetic field depends upon the following, or you can say depends upon so many conditions, like the number of turns of this coil, like how many number of turns are there. So that number of turns is something which is represented by capital N, as I explained you in the earlier unit as well.
Mhm.
Also, it depends upon the length of the solenoid, like whatever length the solenoid possess. It depends upon the current which is passing through the wire. So when we just look at all these things, we simply find out that magnetic field is something which comes out to be mu naught times Ni. Let's talk about it in detail. So here we are going to understand that how this magnetic field due to the solenoid can actually be calculated. So in order to understand it, let me consider a solenoid, and this is something you can assume to be a solenoid. And from one end of the solenoid, I'm assuming that current enters, and from the other end, the current must leave the solenoid. When the current flows through the wires or through the coils, what we observe here is there is automatically some magnetic field set up into the coil.
Mhm.
This magnetic field is something which is parallel in most of the place, but sometimes we may observe it like this. So this magnetic field here, it depends upon the following things. Although we do have derivation of how we got this magnetic field, but here I'm only giving you the formula that which you can directly use in the numericals to find out the magnetic field. So again,
Mhm.
remember the basic things. Magnetic field depends upon length of the solenoid, that is L I can assume. It depends upon the number of turns of the coil, that is capital N. It depends upon the current flowing through the conductor or the solenoid, that is I. So here what we have found is that the magnetic field due to solenoid is something which is directly proportional to the current, which is directly proportional to the small n, where the small n is nothing but number density. We generally use this term to refer number of turns per unit length, like how many turns of the coil we do have in the solenoid in respect to the length. So that small n is something which is written as capital N by L, number of turns per unit length. So when we combine this equation, we find that the magnetic field due to solenoid is directly proportional to N times I. When we remove this proportionality sign, we got a constant into the equation. And that constant is something which is represented by mu naught.
Mhm.
And this mu naught is permeability, which we already know. Again, it is a property of the surrounding space, or you can say it is a property of the medium which is being used in the solenoid. Sometimes, in order to make the strength of this magnetic field more stronger, we replace the we replace the space between the coils with some, you can say, medium, and that medium is something which is used to strengthen the strength of magnetic field which is being produced by the solenoid. So
Mhm.
that strength is something which depends upon this permeability factor. So in order to have a different medium here in this, we can write that magnetic field is something which is equals to mu naught mu r small n I.
Mhm.
Again, this mu r is something we called relative permeability. And this relative permeability is a factor, or you can say it is a constant, which is a property of the medium,
Mhm.
at whichever medium we are using in between the solenoids. So this is how we are going to get the field, and this is how we are going to, and this is the formula which we are going to use in order to solve the numericals as well. So here, a very simple logical question. The question says at near center of the long solenoid, the magnetic field is. So always remember the field diagram. This is a solenoid. When you see such solenoid and you try to draw the magnetic field, at
Mhm.
center there is a straight line, but at the edges it goes like this.
Yeah.
And because of that, the strength at the center of the field, at the center of the solenoid, is very high. So we can say it should be strong and non-uniform.
Mhm.
But if you look at the small section of this side, like this particular section, if I'm talking about, and if I try to draw it once again, so this field line is something like this. So this is something you can call strong and uniform. Where does it exist? At the center only. Remember this. So the correct answer for this particular question is should be strong and uniform at the center. And that is something we are going to witness like everywhere in the solenoid. So remember
Mm.
this. Again, solenoid is a configuration in which wires are bent in such a way that they form multiple coils. And when current passes through these multiple coils, it ultimately shows us magnetic field. Like it
Mm.
ultimately gives us magnetic field at the center. One more question. A solenoid is a long wire wound in a dash form where the turns are closely placed. So, in which form do you actually observe that wires?
Helical.
Yes, correct. Also, if it is circular, it should not be a solenoid. If it is rectangular, again, it should not be a solenoid. If it is elliptical, it should not be a solenoid.
Mhm.
Next, a solenoid is commonly used to obtain a. So for this question, you can remember it. It cannot be electric field. It cannot be electric field. So out of these two, uniform and non-uniform magnetic field, you would always prefer uniform magnetic field
Mhm.
because solenoid is something which is generally we used to get the uniform magnetic field. So
Mhm.
have you seen a solenoid around yourself, like in any appliance or any device?
Mm. Like usually in the back of the door when there's a door stop, I think there I've seen a solenoid.
No, 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 no. It's not. It's not that. In order to see a solenoid, what you can do is you must have seen a motor,
Mhm.
a DC motor, I would say. Uh, Not really. You can see in those remote controlled cars, you must have seen those DC motors. By any chance, have you like broke that motor and see what's inside it?
No.
All right. So what you can do is, it should not be like there only it is there. You can also see it in the phone's charger. When your phone charger got like completely non-functional, what you can do is just broke it, and you'll see that inside that charger there is a solenoid, to be precise, and it is a wire which is like wounded like this way.
Mhm.
And when current passes through these wire, it automatically generates the magnetic field. And these magnetic field are something which we use, uh, which are responsible for the charging of our mobile phones. So always remember, solenoid is something which is used to generate uniform magnetic field. And solenoid is again is a very common. It is a very common component of transformer as well.
Mm-hmm.
In each and every transformer, there is a winding, and that winding is something we call copper winding, and that copper winding is generally acts as solenoid because when current passes through it, a small current when passes through the multiple coils like this, it increases the magnetic field, which ultimately give us more, we can say, amount of current in the circuit because of the magnetic field induced. So there are certain devices in which we do use solenoid to increase the strength of the magnetic field.
Mm-hmm.
The next topic we have is toroid. So toroid is something you can say when a solenoid is arranged in such a way that it forms a circle like this.
Mm-hmm.
So wire and just imagine it this way. There must be some entrance of the current and there must be some exit of the current. So this wire must be arranged in such a way. And here, the most important thing is the magnetic field which we observe is circular.
Mm-hmm.
Whereas in solenoid, the magnetic field which we see is nothing but straight line. So that is the basic difference between toroid and solenoid. It's the orientation that how the magnetic field is being generated. In solenoid, the generated magnetic field looks like a straight line, whereas here in toroid, the magnetic fields look like circular rings. Also, the magnitude of magnetic field here also is mu naught Ni, same as that of solenoid. No change in the magnitude of the magnetic field relation, but the field lines are actually which is being changed, you can say.
Mm-hmm.
So the direction of current is actually something which is going to decide what is the direction of field is going to be inside the solenoid or even toroid. So current's direction is something which is responsible for each and everything. So remember that thing as well. So this is just for the information. As I told you that magnetic field is something which is mu naught Ni, right? But in toroid, if you remember that magnetic field is something which is circular. So in toroid, if magnetic field is circular and we have to find out the current, so current is something which we can say that it is mu naught by mu naught N. Can I say this?
Yeah.
And we have to find here is if n is the total number of turns, the magnetic field of the toroid is. No, we have to find B only, magnetic field only. So it is nothing but mu naught Ni. Now what we can write here is just understand. As I told you that small n is nothing but it is number density. Number density means number of turns per unit length. So I can
Mm-hmm.
write it as number of turns per unit length, that is n by capital L. So I must have written it as n by capital L into I. If you look at the circle and the radius of the let's say toroid is r. So what is the length of this toroid? That is its circumference.
Yeah. 2 pi
What is the
r.
circumference of
2 pi r.
exactly? So out of this, you can find out the correct option. Mu naught Ni by 2 pi r.
So,
Option A and option B both are same.
oh, okay.
Hmm. So this must be the
The
answer.
n looks different. So I was gonna ask what's the difference between the n in option A and n in option B.
No, 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 they are same.
Okay.
All right. If you consider this as well, so n this is the number of total number of turns. So we would say option A is correct as per
Okay.
the question. Yeah, it's a little different. You're right. So next we have to talk about Lorentz force. So as I told you that the Lorentz force is the total force It is the total force experienced by a charged particle when it is placed in both magnetic field and electric field region. So suppose there is a charged particle, small q, and it is placed in electric field as well as magnetic field, like this.
Mm.
So this charged particle is something which is going to experience the force due to both of them. So I can say that the charged particle will experience a force because of electric field as well as magnetic field. So I can say that the F total, or you can say the total force experienced by the charged particle is going to be force due to electric field plus force due to magnetic field.
Mm.
Now, this is something you need to understand, that the electric force which the charged particle will experience, it is nothing but the product of charge into the strength of electric field. Whereas the force which this charged particle is going to experience due to the magnetic field is something product of charge into V into magnetic field. Now again, this particular relations too has proper derivations, but we don't have to discuss them. All we need to discuss is that what is the total force experienced by the charged particle. That F is going to be Q times electric field plus Q times V times magnetic field. Now let us see the each term. So this is electric field. It is magnetic field. V vector is used to express magnetic field. Whereas this V is something which is called velocity of the charged particle. So for a charged particle to experience force due to magnetic field, it must have some velocity, like it must be moving. If it is not moving, it won't be experience any magnetic force. You can assume this. Also, one more thing here that we need to understand is that this Q is something which we already know is a scalar quantity, that is charge. Charge is something which is scalar quantity. But force is not a scalar quantity. It is a vector quantity, so it must have some direction. So this Lorentz force also have some direction. So the direction of Lorentz force is something which is given by the direction of B cross B. Now this is a little tricky here. It is simply representing cross product. So cross product has a direction in such a way. Suppose this is the direction of velocity of the charged particle, and this is the direction of magnetic field. You'll be looking at these cases in the next class
Mm.
more precisely. So here, suppose a charged particle placed at this point is moving towards right and the magnetic field acting towards north direction, you can say. So the direction of force which is being experienced by this charged particle is something which is upward, like that. How you have to find its direction? Just curl the fingers of your right hand from the direction of velocity to the direction of field. And in whichever direction the thumbs point out, it will give us the direction of magnetic force. That is upward. So this is something you can call it. It exists in east. Magnetic field is something which exists in north. So magnetic force is something which must be existing in upward direction. That is out of the plane. And how do we represent this out of the plane vector? Which symbol do we use? Tell me. We saw it
Mm,
in the last class. What is the symbol do we use to represent the out of the plane direction?
mm,
We use dot, whereas cross is something which represent into the plane direction. So remember these directions when we are solving numericals, we'll be using these things directly. Like they won't say that the field is out of the plane. They just give us the direction through these symbols into the question. So we have to
mm,
understand it that if it is dot, so field must be out of the plane. If it is inside, if it is cross, it must be into the plane.
mm.
That is how you can define Lorentz force. The sum of total force experienced by the charged particle placed in electric field as well as magnetic field. So what should be the correct expression for Lorentz force?
Mm.
QE plus QV cross B.
Mm,
So can I take Q as common?
mm.
So the correct expression for Lorentz force is going to be the option.
Are A and B
Remember it.
again?
No, A and B are not same. Understand it. Let me just give you the example to understand that A and B are not same. So suppose this is a plane, all right? And in
Mm,
this plane, there exists a field in this direction, like that. This is magnetic field. Now, I have a charged particle Q, which is moving in this direction with some velocity V. Now, let us try to find out the direction of V cross B first. So, how we are supposed to do that? What I explained? Use your right hand, curl the fingers of your right hand from the direction of velocity to the direction of magnetic field. So, I have
mm.
to curl my fingers this way, like in the
Yeah,
anti-clockwise direction,
yeah.
and thumb will give us the direction of field. So, if you see, the thumb will point out like this, upward.
Mm,
That is something which is V cross B. But if you find out V cross V, so what you have to do? You have to curl the fingers of your right hand from the direction B to V. And if you
mm,
does this, you will see that the field is something which exists downward.
mm.
So it becomes cross, it becomes dot. So they both are different. Remember this. V cross B and B cross B, they are not same, they're different
Okay.
because it will directly going to affect the direction. Now let us try to see that how a moving charge particle experiences a force. So in order to understand that what a moving charge particle experience, it is something because of the magnetic field, you can say. So if there exists a magnetic field, there must exist a force. So let us try to see it. So in order to understand it, we have to consider a charge particle. So let me suppose that I have a charge particle plus Q here, and there exists some magnetic field. I can assume that the magnetic field exists this way. So And the charged particle is supposed to be moving in this direction with some velocity v. So according to the magnetic field, the force, that is the magnetic force, is something which is directly proportional to the magnitude of the charge, that is q. Force is something which is directly proportional to the cross product of velocity times magnetic field direction, like this.
Mm-hmm.
So when we combine these two equations, we'll get Fm, that is magnetic force, is directly proportional to charge times V cross V. When we remove this proportionality sign, we got K here in the equation, and this K in this case is something which is equals to 1. So the magnetic force is nothing but Q times V cross V.
Mm-hmm.
Again, remember this is cross product. As force is a vector quantity, so it must have some direction. And in order to understand its direction, we have already seen it. If there exists a magnetic field in this direction and charged particle is supposed to move in this direction with some velocity. So what you have to do is you have to use your right hand in order to find out the direction. And the direction is given by right hand thumb rule, which we saw in order to understand the direction of field also in the last class.
Mm-hmm.
So I would say just go through the recordings so that you can understand it in a better way.
Mm-hmm.
First, see the recording of the last class, then see the recording of this class again. So it will make it easier for you to understand what we are doing. So in order to find out the direction of magnetic force, you have to curl your fingers from velocity to the direction of field. And
Mm-hmm.
ultimately you will observe that thumb is pointing in the upward direction. So let me write it here. Curl your right hand fingers from velocity to magnetic field direction such that the thumb will point out in the direction of magnetic force. And that is something we call right hand thumb rule. That is V cross B.
Mm-hmm.
So you can also write it as that Fm, that is magnetic force, is in the direction of V cross B only.
Mm-hmm.
So here we have a question. Let us try to answer it. Again, it is based upon the direction thing only. So question says that the motion of charged particle can be used to distinguish between the magnetic field and the electric field in a certain region by firing the charge. Now, let us try to understand it. In order to understand this problem, we have to understand that how charged particle behave when it enters into the magnetic field as well as into the electric field. So
Mm.
basically, we have to understand that in which direction the charged particle actually moves in electric field as well as in the magnetic field. Suppose this is electric field, and in this electric field, I put a charged particle here. So what we know about this? We simply know when we have put a charged particle in the electric field, that if it is positive, it will move along the direction of electric field. If it is negative, it will move in the opposite direction of the electric field. This is something which we already know, right?
Yeah.
Similarly, if there exists a magnetic field like this. So the force will act in the direction of V cross B. It simply means if the charged particle enters into the magnetic field region like this, let's say, with some
Mm.
velocity V. So the force which is going to act, it should be in the perpendicular direction to it,
Mm-hmm.
perpendicular direction of the magnetic field. So the question says we have to answer that how motion of a charged particle can be distinguished when it is put in the magnetic field as well as when it is put in a electric field. So we must say that if we fire the charged particle perpendicular to the field like this, with some velocity v, let us understand it. This is magnetic field and I have put my charged particle perpendicular to it. So what happens here is there must be some force, that is magnetic force, which must be acting again perpendicular to the direction of field as well as the velocity. So that is the appropriate way to distinguish it. Similarly, if we sub if we put the electric field charge in the electric field perpendicular to it, what we will see is either it will go in this direction or either it will go in this direction. The motion would be like that. Whereas in this case, the motion would be perpendicular to both the field and the velocity. Whereas in all the different cases, it is very difficult to guess the trajectory of the charged particle, that how it is going to move when it is being put in a electric field or in a magnetic field. So remember this. This is very important in order to understand the direction of the charged particle, which is put in a magnetic field or electric field. So the answer should be perpendicular to the field. That is the only way to distinguish that whether it is a magnetic field or electric field.
Mm.
Next, we have another question. This question is something which is based on again vectors. We need to understand the vectors first and then we can solve this problem. So the question says what should be the magnetic force acting on the charge? In order to understand the magnetic force acting on the charge, we need to understand that how we can find the cross product. In order to find the cross product, we have to understand that how a vector can be represented. So as we already speak of, that vector is something which might exist in all the three directions. So it is something which is represented by this, like ax, I cap, ay, j cap plus az, k cap. So these I, J, K caps are basically representing the coefficient, or you can say the direction cosines of the vectors in X, Y, and Z axis respectively. Like for example, suppose if there exists a vector like that. So this vector must have component in x-axis, y-axis, as well as z-axis.
Mm.
So the component along x-axis can be represented by ax, along y-axis can be represented by ay, along z-axis can be represented by az. And this is my actual vector. So that ax vector is something which is represented by x direction, which is used here as I cap, and y-axis we use j cap, and in z-axis we do use k cap. So you will be seeing these vector things in the course for sure. Similarly, if we assume that we have another vector, so I can assume that it should be bxi cap, byj cap, plus bz k cap. Again, remember this I, j, k caps are the direction coefficient. It actually represents that what magnitude of vector exists in x, y, z axis respectively.
Mm.
So when we actually have to cross product it, so we write it this way, and it is something which is given by ay, by, az, bz mod I cap, then minus ax, bx, az, bz, j cap, plus last ax, bx, ay, by, k cap. When we solve this thing, this is something we call matrix. And in order to solve the matrix, we have to cross multiply the coefficients like ay into bz minus az, by into I cap minus ax, bz minus az, bx, j cap plus ax, by minus ay, bx, k cap. So when we solve these things, we get the vector, and that vector is something we call cross product vector.
Mm.
So here, what we have given is, we have a speed that is v, 2 into 10 to the power 6 meter per second, along positive x-axis. The direction is something which is represented by I cap.
Hey Sachin.
Hello, sir. How are you?
Hey, I'm good. I'm good. Sorry to interrupt you, but I
No, no
just wanted
issue.
to
Yeah.
discuss something with you. Um, but I didn't want to interrupt you right in the middle of this topic when you're doing it. But whenever you pause, I would like to take a few minutes from you.
Yeah, sure, sir. We can have
Yeah,
that
I
conversation. No
guess, yeah.
issues.
This looks very interesting. Yeah, this remind me of my days studying physics and all the three different directions and how the vectors and uh, yeah, I recollect
Yeah,
all this
things
information.
things
Yes,
things
how we
remain
studied it in
same. It
the
won't
future,
change.
in the past, and then this is very yeah, actually quite a interesting topic. But however, it's kind of new. It's different if someone has not studied these things in the past. So very informative, insightful.
Yeah, it is not easy to understand in the first go. We need to like review it again and again in order to understand, have a better understanding of the same.
That's right.
It's
That's
something
right.
like,
Yeah. Means in the first
yeah,
iteration, yeah, it takes means it kind of goes tangent, just like a vector.
exactly.
Now, what is AXI? What is AYJ? So yeah, three different XYZ, different directions, and how. And well, it's a three-dimensional model. So three directions and how
Exactly.
different.
In the first go, it is very difficult, but yeah, we are trying so that we can have an understanding of it.
Yeah, for sure, for sure. It takes a couple of times. Means first is just I think at least it gets a little bit of it in the head, right? There is something called vector, and then this kind of goes in different directions, and then a person starts building on that one. So Yeah, it's good. Uh, Sachin, another thing that actually I wanted to kind of discuss with you. So
Yes, sir.
initially, when we started this physics in the mid of June, so this week, this is like Ria is between 11th and 12th, right? So she had some plans to do other projects and other internships in summer as well, um,
Okay.
uh, to build her profile. So
Yeah,
she,
I
our
talked.
plan was to sort of like kind of hopefully we would be able to do it like let's say in 3 weeks from mid of June to sort of by the end of the first week of July or so. So in this week
Okay.
of July, Ria is actually supposed to start with the other her other internship actually. Um, and there was a flexibility of a day or two here and there. So she but I wanted to discuss with you. So Ria has to actually attend and go for internship as well. What we were kind of thinking is, I think she got a gist of physics. Yeah, I mean, the best of it. Like if she was able to complete it by, let's say, by this by last week or so, that would have been great. But I think at the same time, probably she got some overview. She is able to probably she got some understanding of what physics is and means what all it involves, and it will sort of help to get her started. Now, because this is kind of a morning time here, this is the time that where she has to go for the internship. So what we were thinking is, can we pause physics here and then she can do it once her either at some other times or in the in semester once her semester starts. Of course, she will be taking probably she'll need one-on-one classes with you. um, so that's what I wanted to update you and discuss with you to see what is your suggestion here. Definitely, Ria likes the classes from you, and your course is very insightful and very miss. It's you are going pretty deep dive and all. So the class is wonderful.
But like I definitely do like the classes from you. You explain things really well. And um I was thinking that either this course could be continued after my like internship is over if my mornings are a bit freer, or during my semester when I have the physics class and I need some understanding on some of the topics, then I could take classes with you one on one for an understanding of the topic.
So Sachin, what is like the other timings that you typically teach?
I do take class from 5 a.m. to like 9 a.m. in the morning here in IST. So we can have that in the evening as well. There won't be any issue. I
I
am
see.
taking
So
classes
if
more
your 9 a.m., I mean, it's our 8:30 p.m.
8:30
Means
p.m.
9
Yeah,
a.m. You finish by 9 a.m. or you even start at
I'll
9 a.m.
finish by 9 a.m.
Okay, so the latest would be like 8 a.m. your time,
Yeah,
right? Which will be our 7:30 p.m.
yes, sir.
Also, I would like to ask one more thing is, like as we were talking in the beginning, it's we are perfectly fine even if let's say you complete partially. I think the main idea here is, let's say on the slide that you're showing, if she understands what these directional component is, these are means if you make it, let's say, for more interactive, and even if you cover let's say 50% of it, I know you may not feel satisfied yourself, hey, if you do not complete let's say the last equation, how it gets calculated. But I think if Ria, let's say in this case, I do not know if she really understood what a vector is or the b vector is. If she did not understand that particular line itself, probably she won't be able to understand the last line of this slide. So if even if you complete, let's say, partial of your slide, but if she gets some part of it in her mind, I think that will be more effective.
Yeah. Let me just give you a small idea about it. See, basically, how I teach to all the AP students is like I have this following assignments. Let me show it 1 second. So these are the assignments. Basically, these are for grade 11th. So before starting with any unit, or you can say starting with any assignment which is being given by the class teachers, usually they just share these kind of assignments with the students. So she must be getting it once she's there in the class when once the semester gets started. So what I used to do is I used to make understand each and every question. And when we are understanding this each and every question before going to the assignment thing, I actually discuss how the equation came and how we are actually going to calculate these particular things. So this is how we are supposed to go, I guess, in the future if we are continuing after the this summer camp thing. And that will something which will really help, like understanding those equations and vectors. See, here, if you're solving like this particular problem, we do need to have that information about that. What is that kinetic energy exactly? If I consider this particular question. So in order to understand it, I'll make sure that she understands the vectors first, she understands what scalars are, how we are going to use these equations to solve and find out the energy and whatever physical quantity which we are talking about in the class. So that is something which will help her once we are starting with the, you can say,
More
mm,
deep dive, or more detailed, right?
the,
Yeah,
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 that's
yeah,
that's what the ask is, Sachin, because Ria has hardly done physics, as I was explaining earlier, right? They, in their high school, she did not do any physics in 9th, 10th, and 11th, because here the curriculum, or probably you are already aware of it, like in ninth
yeah,
she did biology, in 10th she did chemistry, and then 11th she did environmental science, and now in 12th she is doing physics. So here, unlike I think in India curriculum they do physics like
yeah. It's
part of the
compulsory
physics every
for
year,
like,
right?
yeah,
So here it's like a total I think she is able to understand some of it, but it's like that's where she is coming from. So
yeah,
it may become a little bit overwhelming if she kind of misses a part of it. So all our intention is like yeah, if she gets the foundation better, she'll be able to understand the applications better as well.
yeah. Definitely, that is something which is very important.
Mhm.
And once she is starting her school, or you can say the college, then only I can say that these are the things that we need to discuss first before going into the unit, and these are the things that we need to practice before going into the unit again.
Right.
So
So
what
in
we
terms of Ria's schedule, so by the way, you said this will complete with the third module. How many modules are there total?
there are exactly, let me show you for her curriculum.
Yeah, if you go back to the curriculum slide, I know you had shared it in the syllabus in the first class probably.
So we are here exactly right now.
So completing magnetism and electromagnetism.
Yeah, after that we'll be left with like geometric optics, physical optics, wave and sound, and modern physics. So there are four more units, but we can cover them in like hardly 8 lectures.
Ah, okay, okay. All right, all right. And by the way, Ria, are you getting the recordings that Sachin is sharing? Are you getting what? Okay, because probably you can then just for my curiosity, you can send it to me as well. But I did not get it on my Gmail.
Oh, it
But
should be
but
shared.
you
No, no,
have it,
no.
right?
It must be there in your Gmail as well. What you have to do is you just have to open the drive link which I have shared you through the mail.
It's a link
So
to a
that drive will ultimately link to the recordings, so you can
Yeah,
get it
but then
there
I
as well.
should get the link in the email, right?
Yeah, the link is there in the
Yeah,
email
for
only.
some reason I don't see any. Ria, probably you can check because I guess Sachin, when you're sending it to both to Ria as well as me, right?
Yeah, yeah, yeah. I shared both.
Okay, okay. I'll check with Ria. Okay, sounds good. Sounds good. Okay, all right. So, yeah, Sachin, if yeah, today I think almost kind of wrapping up, and then tomorrow, and then we will keep We'll keep you updated. Sure. Thank you very much. So I'll drop now. I'll let you continue today's session, and then But all the my one of the request is, please make it a little bit more interactive and check with Ria, because she is new to physics for that matter.
Yeah, I am trying my best to make her understand each and everything.
That's right.
So
And Ria, you
that's okay.
also, you have any questions? I kind of see Sachin is so supportive, and
Yeah.
I'm sure he will not mind. Even though Sachin, you may feel that, hey, this is kind of probably, let's say, a very basic question.
No, no, no. It's completely
So
understand. I can see, I can sense
please
that.
bear
Hey,
with us,
no,
because
no, no issue. Yeah.
Ria is very new to physics. Okay, all right. Thank you, Sachin. Thank you. We'll keep you informed, and then I'll hang up now. Thank you.
Sure, sir. Thank you so much. So let's get back to the topic. So
Mm,
here we actually have to see that whatever we have given, that those things must have some direction. So just like this velocity, which is along positive x-axis, so it must be represented by I cap.
mm,
Whereas the field is something which is given by this thing, 0.2 j cap plus 0.4 k cap. So what we exactly have to do here is we have to do the cross product of these two quantities in order to get the force. Let us try to do this. So again, as we know that the magnetic force is nothing but it is a product of charge and V cross B. So how we are supposed to do it? Just write this V vector first and as well as B vector. So this V vector is something which is twice of 10 to the power 6 I cap cross product with 0.2 J cap times 0.4 K cap. So let us try to write it first of all. When we are writing it, we can say that this V vector doesn't have any component in Y and Z axis. So we can say that the vector must be 0 j cap plus 0 k cap for the velocity vector. Whereas for magnetic field vector, it should be 0 I cap plus zero point 0.2 j cap plus zero point 0.4 k cap. Now, how we are actually going to do the cross product is, first of all, write I, j, and k cap and write the coefficient of these vectors there like that, zero
mm,
point 0.2, zero point 0.4. Now, this will becomes a matrix, and here there is a charge which is being in product. So, how we are going to solve it? By simply writing it as I cap. Now, just cross multiply these four numbers. If it is I cap, just leave these two things and do the cross product multiplication of these numbers. So we can write it as 0 times zero point 0.4 minus 0 times zero point 0.2. So it will be 0 ultimately. Minus j cap. Again, we have to do the same. Leave this row, leave this column, write these four as a cross multipliers. So we can write it as twice of 10 to the power 6 times zero point 0.4 minus 0 times 0 plus k cap, and it should be twice of 10 to the power 6 minus twice of 10 to the power 6 into zero point 0.4 minus 0 times 0. So once we solve this equation, we'll get the value of force in the vector form only. So it will be like 0 I cap minus j cap, and the product would be 0 0.8 times 10 to the power 6. It will be 0 plus k times twice of again zero point 0.4, it will be zero point 0.8 10 to the power 6 minus 0. So ultimately we'll be having the force as charge times minus j, or you can say 0 0.8 times 6 j cap plus 0 0.8 times into 10 to the power 6 k cap.
mm,
And if you look at the value of charge, that is 2 microcoulombs. So We'll simply put the values here and we'll get F is something 0.2 microcoulomb. 2 microcoulomb is something twice into 10 to the power minus 6. So once you multiply these numbers, we'll get so 0.2 times 0.6. It is going to be negative 1.6 J cap plus again same thing 1.6 times K cap, and there is no I component and it is already 0. So this is going to be the force and this is going to be our answer. Although it's not easy to understand it in the first go, but once you'll be starting with your semester, you'll get the uh, assignments on the I guess on a weekly basis. So when we were discussing those assignments, I'll be able to make you understand these things in a much better way or to a greater extent. And that is something I guess should be more appropriate way to understand these things, because these things are very complex, or you can say very larger. They're there in the very larger extent. So in order to understand it completely, we need to understand that what is the actual need. So if we understand the actual need, we can have a better understanding of these topics. So
Mm.
this is how I said you should go. And we do have following things to discuss here in this class also. And it, next thing here we have is the properties of magnetic field. That what are the properties those magnetic field lines actually exert. So in order to understand its properties, we can actually refer to the properties of electric field. They are quite similar to the properties of magnetic field also. A little bit of difference, but yes, we will see them. One second. Let us see the properties of magnetic field line now. So as you have to discuss the properties of magnetic force, so first of all, it is a vector quantity. So in order to solve the vector quantity, we do use cross product, which we just looked earlier. Second, in order to understand the direction of magnetic force, we use Fleming's left hand rule. So again, it is a little different. Once you're going through the course or once the semester started, I'll try to make you understand it in a better way. Again, remember, if you are writing it left hand, so we'll be using left hand to find the direction. If you are using writing right hand, we'll be using right hand to find the direction. So that is how you can remember it. So these are the basic properties of magnetic force, we can say. So again, let us see a small problem. And here you can see that the current is something which is going through this wire in this way. So because of this current, if you remember, the magnetic field is something which is like that in this direction. Which rule do we use to find the direction of magnetic field? Right hand thumb rule. Remember this. So at the point P, if we actually want to write the direction of magnetic field, so it is something which is going into the plane. So we can represent cross here. So we got the direction of magnetic field, which is into the plane. We got the direction of magnetic velocity like that. So the direction of force is something which is given by this, and we can write it as the force must be in this direction, that is along OX.
Mm-hmm.
So that is something we got from Fleming's left hand rule. See, the thing is, what exactly you need to learn and what I'm teaching, it might be a little different. Like,
Mm-hmm.
I'm covering a little more aspect of these units, but once you're going to the college and understanding the terms and these topics, you might see that what we are doing right now, it's a much more than what you exactly or actually need to learn. So if you're able to understand these topics, what you're going to learn in the college, it will become very easy. So that
Mm-hmm.
will be making like more sense to you once you are going into the college.
Yeah.
Then we are actually understanding that how the charged particle is being in motion when it is in the uniform magnetic field. So it says if the angle between the field and the direction of motion of the charged particle is theta or 180, like that. You can say, suppose this is magnetic field and the charged particle is something which is like going like this way or this way. If it is going this way, so theta should be 0. With the magnetic field, if it is going this way, so theta should be 180 degree. So the force is something which is QV cross B. When we
Mm-hmm.
remove the cross product thing, we got VD sine theta. So if we put the value of sine theta as 0 or 180, you'll get that force is coming out as 0. So if the charged particle enters into the field at 0 degree angle or 180 degree angle, the force experienced by the charged particle is going to be 0. This is
Mm-hmm.
again one such case that how the charged particle is going to move. Similarly, if the theta is 90, again let us look at the equation. It should be QV sine theta. So if
Mm-hmm.
theta is going to be 90 degree, sine 90 is going to be 1, and it means force is going to be maximum. That is the force experienced by the charged particle during that motion when it enters into the field at 90 degree, it will experience the maximum force, and that force is something which is called QVB. We can also find out the radius of the circle. Like for example, if the charged particle enters in the field perpendicular to the direction of the field.
Mm-hmm.
So what exactly happens here is that this charged particle will experience a force in perpendicular direction of the plane. So it must be going this way around it,
Mm-hmm.
like in the circular path. So this circular path must have radius, and in order to find that radius, what you can do is we need to understand the forces. Here, there are many kind of forces which might be acting. The one force it's going to be QVB. The other force which is acting here is centripetal force, which is mv square by r. So when we equate these two equations, like QVB is equals to mv square by r, we get the value of r as mv by QB. So that is the radius of the circle in which the particle is going to rotate once it enters into the magnetic field perpendicular to it. So a little different, a little difficult to even understand it in the first go. But yes, once you are there in the college, you might be able to understand this. We have already done such thing.
Mm-hmm.
We can also find out the time period of the field, time period of the charged particle, that how much time will it take. So as we know that charge is something like speed is something distance over time. So
Yeah.
time can be written as distance by speed. So if we actually look at the distance that the charged particle is going to cover into the circular path, it should be 2 pi r, velocity is v, and we have already seen that what is the radius? Radius is mv by qv. So mv by qv, we can write it in place of radius. Once we solve this equation, we will get the time period of the charged particle which is being entered perpendicular to the field is something 2 pi m by qb. Next, we have frequency, and frequency is nothing but 1 upon time period, that is, it will be qb by 2 pi m. So that is how you can refer to the frequency of the frequency of that charged particle. Next, we have angular speed. Again, these quantities are something which you are supposed to learn in grade 11 if you have taken physics. But as you haven't taken physics, so we need to understand these terms from like very basic. Angular velocity is something which is v by r, velocity per unit radius. So we already know that velocity is v and radius is mv by qb. So omega is something, or you can say the angular speed with which the charged particle is revolving in the circular radius. It is going to be qv by m. So these are the three quantities that we actually want to understand about the charged particle, which is being there in the magnetic field entering perpendicular into it.
Mm-hmm.
Again, we can find the ratios of different particles like proton, neutron, alpha particle, and these quantities or these charged particles are something which are very basic, and you must have seen them in the chemistry also. You can try this out, and if you find that a little difficult, you can discuss it with me. So here we actually have to understand that if the charged particle enters into the magnetic field in different way, so how the path of the charged particle is going to be seen here. So if the particle enters into the field this way, and this cross is simply representing that field is into the plane. Like just assume that this is something the plane, and field is going into the plane like this.
Mm-hmm.
And you simply observe that the charged particle has entered into the field at some angle like this. So once it's entered into the field, because of the field which is perpendicular to the direction of motion, it will ultimately go like that.
Mm-hmm.
This is how the path of the charged particle looks like. So whenever there is a charged particle, whenever it is entering into the field, whether it is electric field or magnetic field, its path will definitely be affected because of that field.
Mm-hmm.
So sometimes it is circular, sometimes it is parabolic, sometimes it is hyperbolic. So there are different cases. In the next case, you can see it. If it is going this way, so it might enter like this and exit the field in that way only. So at whatever angle it is entering, it must be exiting on that angle only.
Mm-hmm.
Similarly, if it is entering perpendicular to the field, it would be experiencing maximum force, and because of that force it will be go like that and come out of this like that. In whichever way it is entering into the field, like perpendicular, so it will exit the field also into the perpendicular direction.
Mm-hmm.
So these are multiple cases. And again, if we assume that it is entering into the magnetic field this way, so it might be possible if it is like this. So it might not be able to completely cross it, but it goes this way because the field is not limited to limited to the infinite region. It is just limited to the small region. Like so, the radius must be greater than d. So the particle which will enter into the field perpendicularly, it will went out of the field like this. So it won't be able to complete the rotation of the circular path. It can't be not be able to follow the path completely. Just let us understand it in a better way. So this is again a field, and the particle enters into the field this way. So it goes here and went like this. So this is how it is supposed to move when it is entering into the field. Next, we can have a question here. So this question says, if the charged particle enters perpendicular in the uniform magnetic field, then energy remains constant but momentum changes. So these terms, again, these terms are something which you need to understand before actually solving these problems. So energy is something which is associated with the work done, that how much work this charged particle is going to perform, whereas the momentum is something that what is the quantity of motion it is going to perform. So whenever a charged particle enters into the uniform magnetic field, there must be energy must be constant, whereas the momentum is something which also remains constant. So we can say option B should be, which is correct. So this is something you can remember it in order to solve the problem. And again, once we are going into the course, we'll discuss these terms in detail if it is required. So we have already seen that what happens when theta is 0, 180 degree and 90. For 0 and 180, it will experience no force. But
Mm-hmm.
for 90-degree, it will experience maximum force. And that maximum force is something QVV. And no force means 0. Then this is the equation of Lorentz force only. And this is the electromagnetic force which actually acts on the charged particle when it enters into the region of uniform electric field as well as magnetic field. Then there is a velocity selector thing. Again, a very important component of cyclotron. This is something which is used to accelerate the charged particle. Like for example, when we want to bombard a charged particle with high speed onto a certain material, what we do is we simply accelerate the charged particle, and that accelerated charged particle is something which is being given by this velocity selector. So we just need to understand that what does it actually do. And here, in order to understand, we need to look at cyclotron. So in the cyclotron, the electric field must be perpendicular to the magnetic field, and because of that only we are able to produce high speed charged particles. So in the velocity selector, electric and magnetic fields, magnetic forces are in perpendicular direction. That is something you need to understand. In the velocity selector, electric and magnetic field are in. So force is different, field is different. They are in opposite direction. That is again a different thing. Here in the previous question, we talked about that it should be force, but here we're talking about the field. So forces should be perpendicular, whereas the field should be opposite, or you can say anti-parallel.
Mm-hmm.
So that is something which is important to understand. So this is something you can try once you'll be going through the recordings, and that will make you easier to revise all these things. And that's all for the today's class. And we'll discuss the last part of this unit into the next class, that is
Mm-hmm.
electromagnetic induction.
Mm-hmm.
Electromagnetic induction is something which says if there is electric field, so automatically it will be responsible for the generation of magnetic field.
Mm-hmm.
Similarly, if there is magnetic field, so that is automatically responsible for the generation of electric field. So that is how we are going to see these things